Hello again. So today we are continuing our discussion on acids and bases. Last time we discussed Bronsted-Lowry theory and we talked about conjugate acids and bases. And today we're going to discuss the strengths of acids and bases. So let's start with acid and base strength. So a strong acid is also a strong electrolyte. And remember that electrolytes are essentially ions floating around in solution. So if a strong acid ionizes completely, that means that it's also a strong electrolyte because we have a lot of ions in solution. So a good example would be hydrochloric acid. And we've seen this example quite a bit. But when hydrochloric acid dissolves in water, it completely ionizes. And then a strong base is also a strong electrolyte because we'll end up with a lot of ions in solution. So a good example of that is sodium hydroxide. So sodium hydroxide will completely dissociate in solution. And down below, there's a table from your textbook listing some strong acids. So you'll notice that on the left-hand side, we have hydrochloric acid, hydrobromic acid, and hydroiodic acid. Oh, looks like there's a little typo there in your textbook, though. It's missing an O. And all of these acids contain a halogen. And then on the right, we have some polyatomic ions. So these would be oxyacids. We've got nitric acid, perchloric acid, and sulfuric acid. And sulfuric acid is referred to as diprotic because it has two hydrogens. So it has two protons that can dissociate in solution. Now, a weak acid is considered a weak electrolyte because only a small percentage of the weak acid is going to ionize in solution. So last time we saw the example of hydrofluoric acid. And I'm going to draw double arrows here because again, this is a weak acid, and what that means is the products, H plus and F minus, could recombine to form the original molecule. So this is actually a reversible process. Now, a weak base is also considered a weak electrolyte because only a small percentage of the base molecules will form hydroxide ions. And this could occur either through dissociation, so if we had something with an OH group on it, or this could also happen if there's a reaction with water. So last time we saw the example of ammonia. And when ammonia is dissolved in water, we get the ammonium ion and some hydroxide ions. And this is also a reversible process. So the ammonium ion we saw last time could act as an acid and give back a hydrogen to the hydroxide ion, which is acting as a base. And then we can reform the original reactants, ammonium and water. So again, this would be a weak electrolyte because we don't see complete ionization of our base. Now down below, we have a table of some weak acids. So we already said hydrofluoric acid is weak. And we'll talk about why hydrofluoric acid is weak, but the other acids that contain halogens are strong. There's also acetic acid, formic acid, and then on the right-hand side, we have some more diprotic acids, and then a triprotic acid, phosphoric acid. And phosphoric acid has 3 protons or hydrogen ions that it could potentially donate to a base. So again, strong acids will donate practically all of their hydrogen ions. And the example we saw was hydrochloric acid. So what does that mean in terms of concentration? So remember that we can express concentration of something by using brackets. So down below we see that if we have a strong acid and it completely dissociates, so let's use the example of HCl again. We're going to end up with complete ionization. So let's say we start with 3 molar hydrochloric acid. So there's 3 moles of hydrochloric acid per liter of solution. When we add that to water, it's going to completely dissociate, so it's going to react fully with water. And that means that at the end of the reaction, we would have 3 moles of hydronium ions per liter of solution. So up above, we see that the concentration of a strong acid is also going to equal the concentration of hydronium ions in solution. And this is going to be important later on when we start discussing things like equilibrium. Now, weak acids, on the other hand, only donate a small fraction of their hydrogen ions. So most of those weak acid molecules do not actually end up donating hydrogen ions to water, which means that we end up with much less than we would if we had a strong acid. So for instance, if we look at our example of hydrofluoric acid again, if we start with 3 molar hydrofluoric acid, in solution, we would have much less than that in terms of our hydronium ions. So the concentration of hydronium ions in solution will be much, much less than the concentration of the weak acid. And again, this will become important later on when we discuss equilibrium. All right, so let's write out some strong and weak acids as well as some strong and weak bases. So I'm going to change my marker color here, and I'm going to split this in half here. And let's put acids on the left and bases on the right. Okay, and then let me change my marker color again, and we're going to put strong acids in blue, and we'll also put strong bases in blue. So in terms of acids, we did see a few strong acids earlier in that table. So we saw hydrochloric acid, hydrobromic acid, and hydroiodic acid, as well as nitric acid, sulfuric acid, and chloric acid. And then for bases, basically, pun intended again, basically anything with a group 1 alkali metal will be a strong base, as well as some of the group 2 metals. So this would be, for instance, lithium hydroxide, sodium hydroxide, potassium hydroxide, and we could keep going. So even rubidium hydroxide and cesium hydroxide are considered strong bases. And then with group 2 metals, calcium hydroxide is strong, strontium hydroxide, and barium hydroxide are all considered strong bases. And again, remember that if you have a metal in group 2 and it forms an ion, we end up with a +2 charge, and hydroxide ions have a -1 charge. So we would need 2 hydroxides for every metal ion from group 2. Okay, so now let's look at some weak acids and bases. So in terms of acids, formic acid is pretty weak. Acetic acid, which is found in vinegar, that is also weak. And then we also saw the example of hydrofluoric acid. So let's see, I'll write the names next to each here, since these are somewhat new. And then for bases, the only weak base that we'll probably use for the time being is ammonia. But in general, any base that has a nitrogen in it is usually pretty weak. So I'll actually add another base that is considered weak. And this is called methylamine. So you'll notice again we have a nitrogen there. So typically if you see a nitrogen in a base, that would be a weak base. Okay, so I would like you to know all of these strong acids and bases, and then just be aware of weak acids and bases. But if you do know the strong acids and bases, you can pretty much assume that any other acid or base is weaker. This will become important later on because we'll need to determine if something can completely dissociate or ionize in solution. And that's going to also have effects on things like equilibrium constants. Okay, so how do we actually determine how strong an acid or base is? Commonly, acid or base strength is measured by determining the equilibrium constant of a substance's reaction with water. So down below we have a couple of generic reactions. The first one involves an acid reacting with water, and then the second one involves a base reacting with water. So just as a refresher, remember that equilibrium constants are written with the concentration of the products above the concentration of the reactants. And then we also would add a coefficient, or an exponent based on any coefficients that we have. Now, if you have a small ionization constant or equilibrium constant, so we're kind of using those interchangeably here, then the acid or base will be very weak. And the position of equilibrium is going to depend on the strength of attraction between the base form and the hydrogen ion. So really, again, it depends on how much product you're forming relative to how many reactants are left. So if you have a really strong acid, then the amount of products will be really, really high. And so your equilibrium constant should be pretty large as well. But if you have a weak acid or a weak base, the amount of product won't be that high, and you'll still have a lot of reactant left. So the equilibrium constant is going to be much smaller. So let's kind of summarize those ideas. And again, this is going to be a bit of review from chapter 15. So if you feel like you didn't have a good handle on chapter 15 material, I would just go back and review that. And if you need any materials from chapter 15, just let me know. So let's rewrite that equilibrium expression. So again, we have the concentration of products over the concentration of reactants. So if K is much greater than 1, that means that reactants are not favored, so products are favored. If products are favored, that means that the acid or base has completely dissociated or ionized. So that means we have a strong acid or base. So as an example, this would apply to HCl. Now, if K is much, much less than 1, the opposite occurs. So in this case, reactants are favored. And if reactants are favored, that means we're not forming a lot of the products. So that means that this would be a weak acid or base. So an example here would be hydrofluoric acid. So hydrofluoric acid does not produce a lot of its ionic products. So we would have a larger concentration of reactants and a smaller concentration of products, and so the equilibrium constant would be much less than 1. Now, if K is equal to 1, we had said in chapter 15 that this means that we are at equilibrium. And neither the reactants nor the products are really favored. So in this case, we would say that we probably still have a fairly weak acid or base. Okay. And again, you can always pause the video if you want to finish taking notes. I guess that's the one nice thing about teaching online is you can kind of control the speed of the lecture. We're not limited to 50 minutes. Okay, so earlier I said we were going to discuss why, for instance, hydrofluoric acid is much weaker than the other acids that contain halogens. So if we consider a strong acid like HCl, HBr, or HI, there is a weak attraction between the hydrogen ion and the non-metal, or in this case, the halogen or halide. So we would get complete ionization in that case. But then if we have a weak acid, such as hydrofluoric acid, there's a really strong attraction between hydrogen and fluorine. So we only get partial ionization in that instance. So now we said that acid strength is measured by the size of the equilibrium constant when the acid reacts with water. So what we actually end up calling that value K is the acid ionization constant. So for instance, if we write out our reaction between a generic acid and water, we would end up with hydronium ions and then our acid ions after losing hydrogen. We could also write this without water, which I also did with HCl earlier. So if we don't include water in our equation, we're really just showing the ionization of the acid. So the hydrogen ion is separating from the rest of the acid. So now we can write the equilibrium constant for this reaction. And again, we want to include products over reactants. But additionally, remember that we do not include pure liquids or solids in our expression. And remember that that is due to the fact that pure liquids and solids, their concentrations do not change during a reaction, so we're not going to include them here. Okay, so down below we can see how we would write the expression of Ka. So we would write the concentration of hydronium ions times the concentration of the conjugate base over the concentration of the original acid. Also, remember that H3O+, the hydronium ion, is also equivalent to any protons that are in solution. So we could also write this expression as the concentration of hydrogen ions times the concentration of the conjugate base over the concentration of the original acid. And we could do the same thing for bases as well. Our expression would just include hydroxide ions and a conjugate acid instead. So your textbook has a table summarizing the acid ionization constants for some monoprotic weak acids. So monoprotic means that there is only one hydrogen on the acid that is lost to solution, or donated to solution. So again, these are all weak acids. We have hydrofluoric acid again, formic acid, and acetic acid. So those were the three that I used earlier. But there are some other weak acids as well, such as nitrous acid, benzoic acid, and hydrocyanic acid. So on the right-hand side, we have a list of acid ionization constants. And you'll notice that all of these acid ionization constants are less than 1. Now, these are also listed in order of decreasing strength. So chlorous acid would be a weak acid, but out of this list of acids, it is the strongest because its value is closer to 1. And then as we go down the list, you'll notice that the values are getting smaller and smaller and smaller, so the acids are getting weaker and weaker and weaker. So, for instance, acetic acid is weaker than hydrofluoric acid and formic acid. So we could compare acids to each other based on their acid ionization constants. Okay, so let's work on worksheet problem 2. And the worksheet can be found on Canvas. So let's calculate the acid ionization constant for the following reaction. Now, just as a quick review, let's identify what is our Bronsted-Lowry acid, what is our Bronsted-Lowry base, and then what is the conjugate acid and conjugate base. So to start, we should know that HNO2 is nitrous acid. So once you have all of the acids and bases memorized, that will be much easier to identify. So that means that water is going to act as a base. Now when we look at the products, we have the hydronium ion and the nitrite ion. So I'll write the name of the polyatomic ion there. So we can see that the nitrite ion does not have any hydrogen atoms attached. So it cannot act as an acid, and therefore it must be the conjugate base. But additionally, if we paired up the acid reactant with one of the products, it would pair with the nitrite ion. And the difference there is a loss of hydrogen. So we can then conclude that the acid has become the conjugate base. Now, the hydronium ion is acidic, and if we pair it with water, we would see that there's an addition of a hydrogen. So this would be the conjugate acid. Okay, so now let's write the expression for the acid ionization constant. And if you would like to pause the video and try this on your own first, you can. So remember that the acid ionization constant has the concentration of products in the numerator and the concentration of reactants in the denominator. So in the numerator, we would have the concentration of the hydronium ions multiplied by the concentration of the nitrite ions. And both of their coefficients are 1, so we don't have to write an exponent. It's just understood that the exponent is 1. And then we're going to divide that by the concentration of the reactants. But in this case, we do have water as one of our reactants, and it's a pure liquid. So we would exclude that from our denominator, and we're just going to write the concentration of nitrous acid. So the next step is to plug in each of the concentrations at equilibrium that are given to the left. All right, so we have 0.02 times 0.02 divided by 0.87. And I didn't include any units here because acid ionization constants, similar to equilibrium constants, are unitless. Okay, so if you want to pause the video and calculate this yourself, you can. The value that I got was 4.6 times 10 to the negative 4th. And if we looked this up in a table, we would find that it should match the value listed. Okay, so we'll end the video here today. I do recommend going over some optional problems from the Tro textbook, 4th edition. If you have an older edition, you can also find similar problems in the back of the chapter. They might have slightly different numbers, but all of the problems that are highlighted in blue have answers in the back of the textbook. So if you do have the 4th edition, I recommend doing problems 33, 35, 37, and 41. These are very similar to problems we've already gone over, and they will provide some extra practice. I will see you in the next video.